All right, so this is the first of two videos about using quadratics for kind of real life situations. So this first one is about a long jumper. Maybe you've seen this at a track meet, maybe you haven't. Basically, they just run and jump into a sand pit and see how far they can go. So we've got this quadratic that somebody has written for us. The equation is there. Where h represents the height of the jump, and then x is the horizontal distance. So this is a function that models height and distance. So of course I want to know how long the jumper jumped. So if you think about that, so our jumper is essentially leaving the ground and then jumping, and we want to know here, right? So this is an x-intercept. Hopefully everybody is okay with that. Some x, and we know that we're on the ground, so the height is 0. So since we know we're on the ground, and we need to find where the point where the long jumper landed, that's the x-intercept. So we're going to go ahead and plug in 0 for y. That's how we find x-intercepts. You guys know that. This is kind of an ugly equation to work with, but since it's an equation, we can do whatever we want to both sides. So I chose to multiply both sides of the equation by 81 times 81 times 81, just so we could get that fraction to go away, which leaves us with just this. And since we don't practice it very often, I know we could use quadratic formula, but since we don't practice it very often, I want to see if this is factorable. But factoring is really hard if that first number is a negative. So I then chose to multiply everything by -1 so that that first term, that quadratic term, would be positive. So that switched all the signs. And then this is not actually so bad to factor. Let me quick make myself a table. So our quadratic term is 4x squared. That can either come from 1x and 4x or 2x and 2x. And then our constant term is a 35. That can only come from 1 and, whoops, try again, 1 and 35 or 5 and 7. And we know since that 35 is negative that this is a difference table. And we are looking for a difference of 68. And if we link together 2 and 35, that's 70. And 2 and 1, that's 2. So 70 and 2 definitely have a difference of 68. So this is one that was factorable. So we know in our parentheses we need to have 2 and 2. And then we need to have 35 and 2. So I've got, oh, moving, there we go. And then I made that 35 negative, so that here would be my negative 70x, and then here would be my positive 2x, and I would get my negative 68 that I wanted. All right, so now we just actually need to solve it. Now that we factored it, how do we solve it? So just one quick thing. So we've got two terms here, right? Two quantities being multiplied together, the green and the pink one there. And the answer is 0, right? It says the green times the pink equals 0, or 0 equals the green times the pink. And the only way that two things can multiply together and be 0 is if one of them, either one of these, is 0. So what we need to decide is what x makes that first one 0, and what x makes that second one 0. And if you don't know that off the top of your head, you can always just see. What makes that first one 0? Well, set it equal to 0 and solve it and see. What makes that second one 0? Well, set it equal to 0 and solve it to see. Oh, whoops, I didn't want you to be able to see the answer. Oh, well. All right, so if we solve both of those, we get these two answers, 17.5 and negative 0.5. So, and I've got the answer up here. I meant to hide it, but it popped up. So let's talk about that answer. So I'm going to go back up to my little picture that I drew. And we're getting that this intercept is at 17.5, 0. That was one of our intercepts. And we also got an intercept back here at negative 0.5, 0. And I know maybe you don't know much about long jump. But if you look at this picture, you can see where this jumper's jumping. There's like a board that they're not allowed, or a line that they're not allowed to cross. And the measurement always goes from that board, no matter how close they were to it. They don't measure it from where their foot left, they measure it from the board. So what that negative 0.5 is telling us is that the foot was 0.5 feet behind the board. So basically that was kind of a poor run because they lost a half a foot. So even though the intercept technically from negative 0.5 all the way between negative 0.5 and 17.5, that's technically 18 feet, but we only measure from the board, so they're only getting from here over. So that's what this little answer says at the bottom, that the long jumper truly jumped 18 feet, however the jump will only count as 17.5 feet, since 0.5 feet of the jump was before the board. Okay? So anyway, this is just using quadratic models. If we know that we want to find where something landed, that's an x-intercept, so we plug in 0 for y and solve. This next problem, still a track meet, but here we have a high jumper, and of course we don't care where the high jumper lands, we care how high they go. So we've got this equation that models how high the high jumper goes, where again h is height and x is horizontal distance. And what we want to know is, can this high jumper clear a bar that's set at 6 feet? So can they get as high as 6 feet? And if we want to know how high they're going, maximum height, that's the vertex, right, of a quadratic. We want to see what the vertex is of this. So we're not going to be plugging in zeros because we're not finding intercepts. We're going to be finding the vertex. And remember, when we have a quadratic in standard form like this, if we want to find the vertex, we do opposite of b over 2a, and then take that and plug it in to find y, right? So that's what I did. Here's my opposite of b, positive 0.62 over 2a, and that gives me negative 0.25, which I then plugged in to the equation, which gets me out 6.2775, okay? So what we're seeing is the turning point of this quadratic, the maximum height, the vertex, is at negative 0.25, which means they're before the bar. That's good. And the highest height they go is about 6.3 feet. So potentially, if their max height is 6.3 feet, they should be able to clear the 6-foot bar. But we know that this max height is not exactly directly over the bar. We're a little bit before the bar. So he's going to be coming down when he gets to the bar. But it's possible he does have the height to get over the bar, since his max height is 6.3-ish. Okay? So again, we were not caring about where he landed this time, we were caring about height. That's why we found the vertex. Okay, this problem is about NASA. I think this is so cool. So it says that NASA creates a weightless environment by flying a plane in a series of parabolic paths. So they go up and down and up and down and up and down and up and down. And when they get to, we have the equation to model the path that they make. But it says that passengers experience weightlessness when the height of the plane is greater than or equal to 30,800 feet. So that's what this red line is going across. So we know that as long as they're above that, they're weightless. I don't know if that's because they shut off the engine and then just let them kind of fly. I don't know how it works. Not a physics major. But anyway, they are weightless as long as they're up above 30,800 feet. And we kind of are curious, how long is that? How long are they like just floating there? So what we need to do is figure out this point and this point. What we need to do is figure out what's that time, that's like time 1, and then what's this time, that's like time 2. And if we could figure out those 2 times that we're at 30,800 feet, we know that in between these times, that's when we are weightless. So if we want to find when the plane is at a height of 30,800, then we're going to go ahead and plug that in for height. And then we'll solve for the time. So that's what I did. I've got 38,000 in for h, and we're going to solve for time. So we'll get one side equal to 0, subtract that 30,000 over. Okay. And then I went ahead and did quadratic formula on this guy, just because the numbers were big and I really didn't want to try and factor. So here's my quadratic formula. I simplified inside the square root. Remember, we always need to start here. So I simplified in there first, which got me down to this guy, which I can then reduce to this, and then I can reduce all three parts. Remember when we reduced all three parts down to these three parts, and that's my most reduced answer. But that, I mean, if we really want to give an answer to somebody who doesn't know much about math, and we say the time was negative 350 plus or minus 70 root 3 over negative 11, everybody's going to be like, what time, what do you mean? So let's just turn that into a decimal. Let's say we just skip all of that. And that's the nice part about word problems, is you don't have to be so algebraically specific. You can just go ahead and tell me what the decimal is, which takes us right there if we had gone back. So basically we're getting that our two times that we're at 38,000 feet are 20.8. So that's up here. 20.8, we're at 30,000 feet. And again, later on at 42.8, we've crossed that height barrier again. So the time in between those, so 42.8 minus 20.8, so about 22 seconds is how long we're being weightless, right? So passengers experience weightlessness for about 22 seconds. If this was me, this is just my thoughts. Not that this is important for the problem, but after about 5 seconds, they probably are vomiting and watching their vomit float around for another 17 seconds before it falls to the floor. That's a side note, we don't really need that. All we really care about is that they are weightless for 22 seconds. All right, so this is just us using quadratic models. If we have a word problem in the model, the equation is given for us. It's just a matter of using it. Sometimes we're plugging in random numbers for y, or sometimes we'll plug in for x. Sometimes we need to find max height. That's what we were doing on this one. We're finding the vertex. Sometimes we need to find intercepts, where things are landing. That's why we're plugging in 0. All of these word problems are going to be slightly different on how you're going to use the model, so make sure you read closely.